So if it's like negative, yeah, it's like negative 2, oh, it's kind of the start. And then I saw that was maybe negative 7. What? I noticed that as well. Because that is another, that's like relative, like, oh yeah, we don't know. That one is maybe negative 3, 4, so do the absolute, or the real absolute. Does that make sense? Yeah.
What?
Hey, listen, hey, no one talk, no one talk. Because I've been working with you all year long and have noticed a few trends, difference between people who are really succeeding on the tests versus those who are maybe struggling a little bit. One key difference is your ability to ask questions. Okay, like some people just are really reluctant to speak up when they can tell it doesn't click. If you can kind of continue to work past that and just wave, speak up, get your friend to ask the question, anything, okay, it makes a huge difference. So this starts out really, really simple, this buff packet, and then it migrates towards some new ideas. Calculus is divided into 2 main topics this class: differential calculus and integral calculus. So semester 1, first 2 terms was differential calculus. Now we're studying integral calculus. But before we kind of get into what's known as integration, just a few reminders. So that's what we're going to do here for a minute. But really, you know, just pay attention to how you're feeling. If it doesn't click, like you can tell, just raise your hand and say, ask me to say it again, you know, whatever. So here we go. First question says, use the graph. So basically they give you a graph and a table. They're talking about an airplane. For our class, all motion is very simple. It's always straight. Nothing complicated. So they're just saying you have a plane and it just flies in a straight line. I had you memorize in first term that location 0 is known as the origin. Please don't forget that. Location 0 is the origin. That doesn't necessarily mean the plane starts at the origin. Okay, and in fact, we're going to say that the plane starts 61 miles from the origin. So you can make up whatever story you want, but we're going to say the position of the airplane at time equals 0 is 61 miles from the origin. We talked about in term 1 that S of 0 means the position at time 0. Wait, if you need me to say any of that again, like it didn't click.
What's the S?
Just the symbol that the AP test will often use to represent the position of an object. So don't tell me why I don't have any idea why they chose S. Maybe because P is used for pressure. So 2 points for Brennan. Anybody else? Please.
So what is the X line representing? Because if the time is at 0, but if it's at 61 at 0, what is the x-axis showing?
Oh, so like in the graph?
Yeah.
So the graph is completely different from this, 2 for Rachel. The graph is displaying the velocity of the airplane. So
Okay.
it doesn't really, the velocity doesn't tell you much about the position. So this is just something I made up.
Okay.
Just an example. I could have picked any number I want. I just chose that one. So good question. Anybody else? Cool. Okay, it says use the graph to identify the time interval when the plane is moving to the right. This is a review question from Unit 1. It's a trick question. It's not meant to make you feel, it's just a trick. Like, who knows when the plane is moving to the right? Who knows why I know when the plane is moving to the right? Who remembers? Hands up. Come on, everybody who remembers. How do you tell when the plane is going to the right? Aiden?
When the graph is positive.
So if the value of the velocity is positive, the plane is moving right. If the velocity is negative, the plane is moving left. So that's why it's a trick question, because the velocity is always positive, therefore the plane is always moving to the right. So for the entire time interval, the plane is moving to the right. How many knew it? 1, 2 for 8. Anyone need me to repeat anything? Please.
So does that not correlate with the slope of graph?
Oh, 2 points. The slope of the velocity graph is the acceleration. So the slope of the velocity graph will not tell you anything about whether the particle is moving right or left. Nothing at all. All you care is whether the velocity is positive or negative. That tells you right or left motion. 2 points. Anybody else? Cool. Second one, B, says use the graph to find the appropriate time interval when the plane is slowing down. Make sure you have this on a flashcard memorized. Speed and velocity are different, but they're very related. Speed is the absolute value of the velocity. So you need to have that flashcard memorized. I think I gave you that in Unit 1 as well. Speed is the absolute value of the velocity. An easy way to think of that is velocity, like if I made a list of velocities, like, I don't know, -10, -3, 2, 8. The positive and negative tells you which way the particle is moving. The number without the sign tells you how fast the particle is moving.
The velocity just adds a direction.
Correct. So speed and velocity are the same thing, except that velocity adds the sign, which gives you the direction. Otherwise, no difference. Anybody need me to say that again, too, for Heather? You need me to say anything different? This one's really about clicking, just like Hadley just did. If you're like, oh, I get it, speed, velocity, easy to understand, then you'll never have trouble again. So just talk until you're really comfortable with the difference between speed and velocity. We lost Allison deep into something on her phone. So hands up, who knows when the plane is slowing down? Talk to each other, raise your hand. When is the plane slowing down? Show me your hands. Who knows? Show me your hands. Who knows when the plane is slowing? Come on, hands. Don't take points if you don't raise your hand. So when is the plane slowing? Anna Kate?
Is it when it's decreasing? The graph is decreasing.
So, stop right here. So about time equals 7.5. Until about here, which is about time equal 27.5. The velocity is, say, 9, 8, 7, 6. So the speed is 9, 8, 7, 6. So the plane is definitely slowing down on this time interval. How many knew it before we said it? Show me. Point to parenthetic. If I need to repeat anything, questions. Do you want to wave so I know I need to say more?
So it's decreasing because the numbers are going down. It's not negative because the absolute value.
Yeah, listen to Elijah. Here's an example that can cause trouble. If I give you a plot of velocity, hold on a second. And the velocity plot looks like this. I want you to vote, please. One means you look at this plot of velocity and you tell me the speed is increasing. That would be this vote. This one would be you look at this plot of velocity and you tell me the speed is decreasing. Show me your vote. Is the speed increasing or is the speed decreasing? It's a good check if you're really understanding the concept. 2 points for everyone for voting. Okay, the velocity here is, say, -1, but that means the speed is 1. Now the velocity would be -4, but the speed, therefore, is +4. Now the velocity is, say, -9, but the speed is +9. So for this example, the velocity is decreasing, but the speed is increasing. You need me to say it again or different? Is that what you meant, Elijah? Okay. Awesome. Next thing. So I already mentioned this. The symbol represents the position. So S of 0 is the position of the plane at time equals 0. And we're just going to use a made-up example of 61 miles. Nothing in the problem tells you that. I'm just making that up. So. What is the meaning of S of 40? So that's the position at time equal 40. We'll not worry about what that position is for a minute. Oh, here they give us an example. They say, oh, the position is 234. Then they said S of 0 was 10, so the change in position would be 224. So I guess I should be more consistent with what I've got on the worksheet here. Make this 10. Didn't notice that. Okay, please wave if you'd like me to say more about the difference between. So here's the key concept. Let's make sure you are understanding the difference between speed and velocity. We already talked about that. And you're also understanding the difference between the position versus a change in position. You want me to say more, please?
The S of 0 is just a position equation, right?
So S of 0 isn't a position equation per se. It's an example of a specific position. So it's saying when time is 0, the location of the plane is 10 miles from the origin. 2 points. You want me to say more, please?
Can you find like that it's 10 on the graph, or is it just because it told you?
Oh, outstanding. 2 points for Brennan. You cannot determine S of 0 equaling 10 from the graph of velocity. It's not possible. So there's no way to know the position of the object simply by knowing the velocity. Common sense tells you that is true, because if all you know is the speed and direction of an object, you have no idea where the object is located. Please.
So how do you find it? Or do we just have to wait till they tell us?
So sometimes they'll just have to tell you. They really won't give you enough information to find the position. Going back to Hadley's comment, if they had given you an equation for a position, you could use that position equation. If we had something like, say, this, I'm just making this up, but if they give you S of t equals 3t squared minus 5t, something like that, plus maybe 10, I don't know, then you can use the equation to find the position, but otherwise you wouldn't be able to. Please.
So if you're trying to find the position at some point, wouldn't you just, it's whatever the slope at one point is on the graph, pretty much? It's like the derivative.
2 points. You're just mixing that up. So the slope of the velocity graph is the acceleration. So the position, the slope of the position graph is the velocity. And then the slope of the velocity graph is the acceleration. So no, I can't find the position from the velocity graph, but I can find the acceleration from the velocity graph. 2 points. Anyone else? Cool. Next thing. Simple example down here. It says the expression, therefore, S of 40 minus S of 0 is known as the change in position or displacement of the airplane during that time period. They give another example. They say if S of 20 is 152, calculate the change in position from time 20 to 40. Raise your hand when you have that. Don't spend too long. But who has the change in position from time 20 to time 40? Change in position from time 20 to time 40. We should get the whole room to raise your hand on this one. Talk to each other until everybody raises their hand. What's the change in position from time 20 to time 40? Look at your hand out. Use your calculator if you need to. What is the change in position from time 20 to time 40? Show me your hands. Who's got it? Trey, what do you got?
82.
Trey says 82. Show me your hands, please, if you agree with Trey. Show me your hands. 2 points for Trey, 2 for the rest of it. Questions? Please.
So normally when you're finding like, I guess like a change in a graph, like the slope, kind of, you know what I'm saying? You divide it by the y.
Outstanding.
Why not do that?
Hey, listen, come on. Hadley's pointing out a key difference. It's a very good question. In this instance, we are talking about change in position. We don't have a graph to look at. We just have some numbers. What you're referring to is rate of change.
Right.
So if you're looking for a rate of change, it has to be a ratio. It has to be something divided by something. But this is just the change, so just a subtraction. So a change is a difference or subtraction. A rate of change is a division. This divided by this. Is that what you meant?
Yeah.
There you go. Cool. Next thing. So we already did that. Okay. Same graph, same table. The question says, identify the time interval when the airplane is speeding up. Show me your hands if you know that. What is the time interval or intervals when a plane is speeding up? What's the time or time intervals when the plane is speeding up? Let's go, Grant.
From 0 to 7.5 and then 27.5 to 40.
Who agrees with Grant? Show me hand. Point 2 for Grant. Question? Awesome. The next 2 questions are kind of dumb. That's for the smiley and frowny face. You had to know in the last test that the object or plane is at rest when the velocity is 0. Well, if the plane is flying through the air, I would hope the velocity is never 0. So the plane's never at rest. If it is at rest, it stalls and falls to the ground. Stalls and falls. So dumb questions. I'm not sure I put those on there, but I was in a weak moment. So. Questions? Please.
So what does happen to the plane when the slope goes to 0? So,
Right here.
Yeah.
Good question. Hey, because it's a graph of velocity, what happens at this moment is the acceleration of the plane is 0, which means at that instant the velocity is not changing. But it's only for a given instant. The velocity is increasing. Then for an instant the velocity isn't really increasing or decreasing. Then it switches and starts to decrease. So that's all that happens right there. 2 points.
So if we're looking at a velocity graph for the same problem, would it be at the 0 there? Would
So
A of
this-
t be at 0 if we had?
There we go. Let me say it back to you, and if I let's just keep talking for a minute. So this is a velocity graph.
I would say the acceleration.
Gotcha.
Would the acceleration be 0?
Correct.
On the graph.
So right there, the acceleration would be 0. Right here, the acceleration would also be 0.
Okay.
That's perfect. 2 points. Okay, next thing. Okay, ignore that one for a minute. We just got to work on a blank sheet for a second. So, actually, no, I want to use this. Wait a second. Let's go here. There we go. Okay, new idea. The new idea is known as integration. We've studied differential calculus for the first 2 terms. In term 3, we study integral calculus. So 1 and 2 were differential calculus. Now we're studying integral calculus. Right here, the velocity is 7 miles per minute. The velocity is changing. It's increasing, but it's a little hard to do computations with something that's moving. So we're going to make kind of an estimate here. We're going to pretend that the velocity is 7 miles per minute and that the velocity remains at 7 miles per minute for 2 minutes. Okay? That's not what really happens. The velocity is steadily going up, but we're going to pretend that the velocity stays at 7 for the first 2 minutes. More like that. The graph would be the red graph. The velocity is just steady at 7 miles per minute for 2 minutes. Okay? I told you before, you cannot find the position from a velocity graph. Don't try. It's not possible. But you can find the change in position. That's why it's critical you know the difference. Position is where the plane is located. Change of position is like knowing by how much does the position change. So if the plane has a, don't think too hard on this, just raise your hand. If the plane has a velocity of 7 miles per minute for a time period of 2 minutes, raise your hand and tell me, by what amount does the plane's position change during those 2 minutes? This is not a trick. I just want to make sure you're following me. Drew? How many knew it was 14? 2 points. So 14 miles. Okay, then we're going to say after 2 minutes the velocity suddenly jumps to about 8. And stays at 8 for about another 2 minutes. So now we have 8 miles per minute. I multiply that by 2 minutes. I end up with 16 miles. So the change in the plane's position during the next 2 minutes. Questions, thoughts? Anyone need me to repeat? Elijah?
So are we just making these numbers up? Kind of.
So we're really reading the graph, but we're just kind of jumping. Because I don't really want to go, the velocity really is like 7, 7.1, 7.2, 7.3, 7.4, 7.5, etc. So I'm just going to say, yeah, as a rough estimate, let's just make the velocity 7 miles per minute for the first 2 minutes.
Okay.
And then it does jump up to 8 after about that. So that part I'm just reading the graph. So part of it's kind of random, part of it's following what the graph says. Does that make sense? 2 points. Anybody else? Solid. Okay, then the velocity jumps up again, if we kind of make an estimate, to maybe about 9. And then we'll stay there for 1 minute. So we'll say the velocity is 9 miles per minute. For 1 minute. So during that 1 minute of time, the plane's position changes by 9 miles. Questions? Cool. So over the 5-minute period, the change in position the delta S, oh, that's a terrible delta, try that again. So the delta S, the change in position for t equals 0 to t equal 5. Again, don't think too hard, just raise your hand if you can tell me. What's the total change in the plane's position during that 5-minute time period? Hands up, come on. What is the total change in the plane's position during those 5 minutes in total? Isaac?
39?
How many agree?
20.
39 or which one?
39.
How many agree? 0.2 for Isaac. Okay, so here's the good news. Integration is not something that's really new. Like you all understand this, we're just multiplying, and we're multiplying again, and we're multiplying again. After multiplying, we just add them up. Okay, integration is a mathematical operation that just combines those operations into one. So integration is a combination of multiplying and adding, and that's all it is. Just multiplying and adding. Questions? Please.
So like that number can't be like perfectly accurate to like the actual speed or like the actual distance covered though, like right? Because at some point when we calculated it moving 7 miles, was it going like 7.5?
3 points for Isaac. Everyone hear what he said. Perfect. Perfect. This is really an estimate because we fudged, right? We said, hey, let's just pretend the velocity is 7 miles per minute for an entire 2 minutes. It really isn't. It's 7, then it's 7.1, 7.2, 7.3. So if we want a more accurate estimate, what we have to do is many more computations. We have to say, well, the velocity is 7 for 1 second. And then the velocity is 7.01 for another second. Then it's 7.02 for another second. If we do hundreds of computations, we get a very accurate depiction of the change in position. Our depiction is just a rough estimate. You need me to talk more about that, please.
I'm just saying, so if you take the velocity slope and then you shade the area underneath it to the origin, would that actually be the displacement?
If you've had physics, they talk about that. It's perfect. And it is true that the area you see between the velocity graph and the x-axis coincides perfectly to the change in position. It absolutely does. It's perfect. We'll talk more about that later, but it's perfect. 2 points. Anybody else? Okay, we got 30 seconds to memorize this symbol. Here's the symbol. We're taking velocity and we're multiplying velocity by a change in time. So neither of those symbols is new. We just never put them together. Here's velocity, here's change in time. Ideally, it's what Isaac said. Don't leave on the bell. Stay with me for just a few extra seconds. Ideally, we want the change in time to be really, 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 really small. But sometimes that's hard, so we estimate by making the change in time bigger. Everybody good here? Notice how they're multiplying just like we multiply? After you multiply them, you need to add them up. So this symbol is a large S, or sum. Add them up. You do it from time equals 0 to time equal 5. This is integration. And this integral is equal to the change in position.
Okay,
You
can
can
I
go.
have the
Thank
college
you.
students come down to
Good
the main
work.
office?
No homework
Next
tonight.
Mason.
No homework, just keep the packet for next time. So.
Paul Johnston,
Good work.
Avery Webb, Aaliyah Harris, Sam Fresh, and Carson